Okay, so to reiterate briefly, our real interest is in knowing what the mean of a population is, or what the proportion of an entire population is if we're working with a binomial variable. Mean for a numerical variable, proportion for a binomial variable, okay, or a percentage. So we're interested in knowing what the population mean is, but unfortunately, most of the time we're never going to actually be able to know that without measuring everybody in the population. So we want to have a tool to be able to estimate what the population mean is likely to be and how confident we are that we've actually captured the population mean. So the way we do that, we use a technique called confidence intervals. So the confidence interval is going to consist of when we take our sample from that population, that we're going to add and subtract an acceptable margin of error from that mean, and then we're going to say that within that range, that lower number to that higher number for the margin of error, that within that range we have a certain level of confidence that we know that the mean is somewhere in there. Okay, so for the most part, it's usually going to be either 99% or 95, most likely, most often, or a 90% confidence that we've captured the mean. Okay, so, and the way that we're going to calculate that is we're going to take advantage of our understanding of the variability of the numbers in the sample that we took, right? So most of the time, another thing that we won't know about either these populations, the numerical one or the binomial one, is we normally won't know what the standard deviation, sigma, is for those populations. If we do know it, it simplifies things quite a bit. But often, the only way we can actually know it is if somebody else has done a very large study and we're willing to accept that we have some confidence that we really know what it is. Okay, but for the most part, most often we really don't know what it is. Okay, so if we do know what it is, that margin of error is equal to the standard deviation of the population, if we know it, over the square root of the sample size. Our guess at the mean becomes less and less uncertain the bigger the sample size is. So our margin of error gets smaller because the bottom here gets larger. So our margin of error is equal to the standard deviation over the square root of the sample size. If we don't know what the standard deviation is, then the only way we can get a handle on it is to take a look at the standard deviation of the sample and use that instead of the standard deviation of the population. Because like x bar approximating mu, the standard deviation of the sample approximates the standard deviation of the population. So we can use the standard deviation over the square root of the sample size instead. The only problem there is that it adds a bit of uncertainty to us. So in order to calculate our confidence interval, instead of using the z-score that corresponds to each of these levels of confidence, we have to use a t-score, which is based on the sample size. And that t-score is always bigger than what the z-score is. For instance, for a 95% confidence interval, z is equal to 1.96. Number of standard errors, number of standard deviations or standard errors of repeated samples that we have to go to the left of the true population mean and the right of the true population mean to capture 95% of the samples means that we would get if we repeatedly took samples of size n from that population. Now the t-score, because we don't know the standard deviation, sigma for the population, well in that case we have to use the standard deviation of the sample instead. So that standard deviation introduces a bit more uncertainty for us. So the t distribution actually represents an accommodation to that uncertainty. So t, for instance, depending on the sample size, is going to be a different quantity, right? It might be 2.3, it might be 2.1, it might, if it's a very large sample size, it might be 1.98. The bigger the sample size is, the more certain that we understand what the standard deviation is, or the better estimate of the population standard deviation is, and the smaller that t-score becomes. It never really becomes 1.96 unless you sample the entire population or infinity, right? So that's the way we're going to calculate that. So it's kind of a little abstract right now, right? We do the same thing with the proportion of a population. In other words, let's say there's 1 million people in a population. And we went and checked every one of them, and we found that 350,000 of those people got a flu shot this year, right? So the proportion of the population that got a flu shot is 350,000 out of a million is equal to 0.35. Well, chances are we won't have the resources to go and survey everybody. So we might survey 100 people from this population. Now, we would expect if the proportion of the population is 0.35, we would expect 35 out of 100 people to have gotten a flu shot, right? 35 out of 100. Okay, however, we'd have to be awfully lucky to get exactly 35 out of 100, right? Sometimes we might get 34 or 35 or 37 or so on and so forth, right? So when we do a sample, we might get a slightly different number, sample of 100. We might wind up with p for that sample being equal to, let's say, just for argument's sake, let's say we get pretty close and it comes up to 0.34, 34 out of 100 people. Instead of calling that p, we call that p cap, just like we call x bar instead of mu, the mean or the proportion for a sample, right? So we need the same thing here. If we want to know how well we know that, we have to add and subtract the margin of error that we need to accommodate the level of confidence that we want. So for 95%, we would need to add and subtract. Okay, well, what are we going to add? What do we need to add and subtract? Well, we're going to add and subtract the t-value that we need times the standard error. And the standard error in the case of numerical variables is sigma, or the standard deviation over square root of 1. In the case of proportions, it's equal to the standard error in the case of proportions is equal to the p times 1 minus p over the sample size and the square root of that whole thing, right? So that's how we calculate standard error. And the margin of error is equal to the t-value for 95% times that standard error, whatever that turns out to be. Now, because we're almost always taking a large sample when we're taking a proportion, we're at the numerical variable, we might be taking a much smaller sample. Because we're almost always dealing with a large sample, right? At least 15 on each side of the proportion. When we deal with proportions, for convenience, we often just use the z-score, 1.96 for a 95% confidence interval, instead of bothering with the t-table, because we're usually dealing with a large sample again. Okay, so let's do an example of this. And then we're going to move on to hypothesis testing. I just want to go back and backtrack a little bit, and then we can go forward. Okay, how are you guys doing online? Any questions so far? Will I be discussing the final project as on syllabus? I'm going to hold off for another week or two on that. You'll have plenty of time to work on it. It won't be that intense that you have an issue with it. But the reason why I want to wait another week or two is because I want to introduce you to the databases that you're going to be working with or that we're going to provide you with. And we really haven't covered some of the statistical techniques that you're going to need to do that project. So it's a little bit premature to make up your mind on it. Well, the due date will be the end of the semester, so I don't think we can adjust it unless you guys want to keep coming here in January. So it's basically the due date, the absolute final due date for the project would be the last day of the semester. Okay, so, and I'm also going to give you guys an option for you guys that are doing the course online. You will have an option of taking a third exam with the last part of the material that we cover after exam 2, instead of doing a project. So you'll have that choice as well. Okay, so I wouldn't worry. It's a little premature to worry about that right now. So we have plenty of time to worry about that. And we will be worried, trust me. So at any rate, I hope we won't be worried, really. So at any rate, so let's do a concrete example of this. Okay, let's say I tell you that we take a sample of size 64 from a population, random sample from a population, and we measure some numerical variable for that population. Let's say it's BMI. And we find that the average BMI for that sample is equal to 2.8, right? So let's say I told you, well, this population of athletes, for instance, playing football, NCAA or NCAA basketball, that we know from other studies that the standard deviation for the BMI for that population, for everybody for all those basketball players in the NCAA, that standard deviation for all of them, for whatever reason we might know it, is equal to, say, 0.5. Okay, so now you can, based on the sample that we have, 64, we can go ahead and calculate our confidence interval. Our confidence interval is going to be equal to x bar plus or minus our margin of error. Now, our margin of error is either going to be a z-score or the t-score that we need for I'm going to call it a 95% confidence interval, right? So in this case, since we know the standard deviation of the population, we can use the z-score. So you guys remember what the z-score is for a 95% confidence interval is? 1.96, right? 1.96. For a 99% confidence interval, it would be 2.58, right? And for a 90% confidence interval, it would be 1.64. But I'm just going to do 95 for now. So it's going to be 1.96 times the standard error. So what's the standard error equal to? Standard error, when we work with numerical variables, and we know sigma is equal to sigma over the square root of n, right? So that's going to be equal to 0.5 over the square root of 64, right? Which is equal to 0.5 over 8, right? So that means it's equal to 5/8 is what? 0.625? Yeah. 0.625. Yeah, we got a couple of carpenters here, right? 0.0625. Oh no, 0.625. 0.625, right? Am I right about? Oh, I'm sorry. It's 0.5. You're right. Yeah, it's 0.5, not 5. 0.5. 0.0625. Okay, that's our standard error, right? So our confidence interval is x bar plus or minus 1.96 times 0.0625. Okay, so let's calculate first the margin of error that we're going to add and subtract. It's hot in here, right? Isn't it? Okay, let's see. Okay, 1.96 times 0.0625 is equal to 0.1225. And I'm going to put that into memory. And then I'm going to multiply it by 1.96. Let me recall it. Times 1.96. Did I already count? I already multiplied by 9. I already did that. Okay, so that's equal. What was it again? Let me get it again. 0.1225. So it's going to be, it's x bar, which is, what is x bar again? It was 2.8, plus or minus oops, I did something wrong there. I must have clicked it. Oops, I cleared it. Let me do it again. 1.96 times 0.065. Okay, well, that's wrong. Hang on a second. Got to clear everything out here so it comes out right. 1.96 times 0.0625. Bingo, there we go. And let's put it into memory. Clear. Okay, so I'm going to take 2.8 and I'm going to subtract that margin of error from it. And that comes out to be I'm going to call it 2.68. Okay, I waited until very last calculation before I bothered to round anything. 2.68. 2.68. And now we're going to try adding it to our 2.68. Clear? 2.8 plus our margin of error is going to be 2.92. Okay, so basically what we're saying now is that we're 95% confident that our true mean for the BMI of all of these athletes in this population is equal to is between 2.68 and 2.92. We're never going to be sure. I could make this confidence interval wider by using 2.58, which would make it a 99% confidence interval, but I'm never ever going to be completely sure I've captured it 100% unless I make it so wide that it really doesn't help us at all anyway. So now, what if we didn't know that the standard deviation of the population was 0.5? What if the 0.5 was what we got from the sample? In other words, the 64 people that we sampled, the standard deviation for them was 0.5. Well, we do exactly the same thing. X bar plus or minus, except this time we would use a t-score instead of a z-score. T-score for, I'm going to put for alpha over 2 is equal to, for alpha is equal to 0.05. I'll put 5% chance of being wrong, or a 95% confidence interval. Okay, and we're going to use a t-score times our standard error. Now, since I use the same number, it's going to be standard deviation instead of sigma. So it's still going to be 0.5 over the square root of 64. It's still going to be 0.0625, right? Because I didn't change that number. But now this t-score has to be different. Okay, and where are we going to get that t-score from? I think I have it in the folder on the desktop. Press the t-table. There we go. Okay, we go to a t-table, and we look up the value for that t-score. For a 95% confidence level, right, it's going to be in this column. And we're gonna find the sample size here, except instead of sample size, we're looking for degrees of freedom, which is the sample size minus 1. Well, in fact, that's so large a sample that chances are it's not going to give us 63. The closest one is going to give us is 60. So I'm going to use 60. And it appears that the t-value is 2.0, right? It's more than z would have been, right, 1.96, but it's going to make our interval a little bit wider. Oops. Okay, so let's go in here. So it's going to be 2.2.0 times 0.0625 is going to be our our margin of error. So let's give that a try. 0.0625 times 2, okay, is 0.125. I'm going to clear out memory, and I'm going to load this into memory. And I'm going to go back. 2.8 minus our margin of error is 0.267. Not much of a difference, right? Because the sample size is so big. 2.67. And I'm going to add it. Oops. Lost track of my mouse. Oh, you know what it is? It kind of on the pad there. Okay, I'll clear that. 2.8 minus our margin of error, and it's going to be 2.8 plus our margin of error. It's going to be equal to 2.93. I'm going to round it up. 2.93. 2.93. So you can see that our margin of error is just a little bit wider than it is for if we knew the standard deviation and used of the population and used the z-score. Now, it's going to be quite a bit wider if the sample size is smaller, right? And that's because if the sample size were, say, only 10, right? Well, sample size of 10 is 9 degrees of freedom. Well, now the t-value would have been 2.62 for 95%. So when you multiply that times the standard error, gives you a bigger margin of error, and you're subtracting and adding a bigger number. So it makes the interval wider. You guys comfortable with that? You guys okay with that? Okay. Now let's try one with a proportion. Okay, let me switch papers here. Whoops. Okay, so now we're going to take a little one with a proportion. So now let's say that I take a sample of, let's see, let's take an interesting sample size. 225. Take a sample of 225 people, and I asked them if they've ever been told that they were diabetic. They've been diagnosed as being diabetic. And out of the 225 people, 50 people say that they've been diagnosed as being diabetic, right? 50 out of 250. So the proportion in this sample who are diabetic is 50 out of 225 people. That's our P cap. We don't know what the proportion is for the entire population. Let's say that this is all residents of senior care facilities, for instance, right? We didn't sample all of them. We just randomly sampled 225. So let's find out what that proportion is. 50 divided by 225, 225 is equal to 0.222. 0.222, about 22%, a little bit more than 22% of the population of the sample is diabetic. What about the population P? What do we know about that? Well, we don't know what that is. All we know is what we know about the sample. So we're going to generate a confidence interval. And our confidence interval is going to take our proportion for our population, right, P cap, and we're going to add and subtract our margin of error. Okay, what's our margin of error? That's equal to P cap plus or minus. And now, do I use a t-score or a z-score for a proportion? I use z-score. Why do I use a z-score? Because I'm working with a very large sample. Remember how close it was even with a sample of just 64 people? Now it's going to be even closer to what we would get as a z result when we're talking about 225 people. So we're going to use a z-score. And for a 95% confidence interval, what z-score do I use again? Yeah, exactly, 1.96. Okay, 1.96 times the standard error, right? Right, my margin of error is 1.96 times standard error. So now let's calculate standard error. The standard error for proportions is equal to the square root of p times 1 minus p over n. Okay, so in this case, it's equal to the square root of 0.222 times 0.788. No, that's going to be too much. 778. Is that right? Add those two together. Carry the 1, it's 9. Carry the 1, it's, yeah, I think that's right, right? Okay, over the sample size, which is 225. Okay, so let's work that out. Okay. All right, let's see. Let's clear all this stuff out. Okay, so we got 0.222 p times 1 minus p, which is 0.778 equals this, divided by the sample size, 225. And now I'm going to take the square root of that whole thing. And it comes out to be 0.0277. 0.0277. Okay, that's going to be our standard error. Okay, so now I go back here to my formula, and P cap, right? P cap is equal to 0.222 plus or minus 1.96 times the standard error, which is 0.0277. Okay, so let's work this out first. Plus 0.222 plus or minus 1.96 times 0.2777. I actually have it in here, so I don't have to bother to round it. Times 1.96 equals 0.054, about 5.4%. So I am going to clear memory, and I'm going to put it into the memory, and then I'm going to clear the register, and I'm going to take my P cap, 0.222, and I'm going to subtract my margin of error, and it's going to be equal to 0.168. 0.168, and the upper limit for our confidence interval, oops, is going to be 0.222 plus our margin of error. That's going to be equal to 0.276. Okay, so where are we now? Where we are now is that we're 95% certain that the true p-value for the entire population is between these two values, 16.8% and 27.6%. Before, all we knew is that for our sample that we found the mean of 0.222. We thought maybe that would be a pretty good estimate, but now we have actually quantified with some level of certainty where the actual mean should be. Okay, so now we're going to take that one step further. And we're going to say to ourselves, since all we're doing here is adding and subtracting basically roughly two standard errors from our value that we find for our mean, that maybe I can use this to compare two populations. And the way that we're going to do that is we're going to start with a situation where we have two populations, population 1, right, which has a mean of, let's say 100, and population 2, which I don't know what the mean is, right? For some reason, they've done like a census, and they know that the mean blood pressure, I'm going to call that blood pressure, for population A, I'll call that, now our other population, population B. For that population, they happen to know that the mean value for the blood pressure for the entire population is 100. For our population B, we don't know what it is, but we want to compare the two of them. See how likely it is that both populations have the same mean value. Okay, so how would we express that? That the two populations have the same mean? Well, we'd create something called a null hypothesis, right? And then null hypothesis is that the mean for population A is equal to the mean for population B. Okay? If it's equal or the same or no different, we call it a null, right? Null hypothesis. Well, now how about, what are we trying to prove though? We're interested in proving maybe that those two populations have different mean blood pressures. So what we're trying to prove is an alternative hypothesis, that the mean for population A is not equal to the mean, for population B. Okay. Now, how are we going to do that? We're going to do that by demonstrating that the mean for population A, which is known, is more than 2 standard deviations away from the mean for the sample that we take from population B, from the other population. Okay, so let's take this population here. Let's say we take a sample from that population. And that sample from that population, right, call it population A, sample population B, the mean for that sample is 90. And the standard deviation, I'm not going to make believe that I know sigma. If I know sigma, I can use the z-score. But I'm going to make believe that I don't know sigma, and I'm going to say that I take the standard deviation of my sample. My sample size happens to be, I'll call it 25. Sample size is 25. My standard deviation for my from population B, random selection, 25 people from population B. My standard deviation is equal to, I'm going to call it 10. Okay? So, in order to determine whether these two are different, how likely it is that they came from different populations, I'm going to see if they're really two standard errors apart. Same way we calculate 95% confidence interval, except this time we're comparing a number to the results of a sample. So how am I going to do that? Well, I'm going to actually measure what the z or t score is for the number of standard deviations. Remember, z or t is really basically the number of standard deviations apart. A couple of things are, right? So either z or t. In this case, since it's a small sample and I don't know sigma, I'm going to use t. So I'm going to calculate a t-score. And that t-score is going to be equal to the difference between the two means, my x bar, minus the mean of the population that's known, the known value, over the standard error. Well, what's the standard error? How do I calculate the standard error? I calculate standard error is equal to sigma over the square root of n. If I don't know what sigma is, I use the standard deviation over the square root of n. Well, in this case, the only standard deviation I know is from the sample. So I use standard deviation, 10 over the square root of 25, which is 5. So the standard error is equal to 2. So let's see what I wind up with here. My t-value is equal to x bar. I'm going to change something midstream here because I want this to be a little bit more interesting. I'm going to call this 96 instead of, or 90, I'll tell you what, call it 97 instead of 96. It's going to be x bar minus mu, which is 97 minus 100 over my standard error, which is equal to 2. Okay, that's the number of t-scores apart that they are. That's going to be equal to 3 over 2. It's going to be equal to, actually it's going to be equal to minus 3 over 2. It's going to be equal to minus 1.5. These two values, the mean for my sample, mean for my population, are 1.5 standard errors apart, t-scores apart. So let's see what t-value I need to be 95% certain, right, with that sample size. So I go to my t-table again, right? And again, because I want to be 95% certain, less than 5% chance of being wrong, so now I'm going to introduce this idea of alpha error. My alpha error is the probability that I'm willing to accept that I might be wrong. For 95% confidence, an alpha would be 5%, 0.05. So I'm going to go to my t-table in the same column for 95% confidence. I'm going to go down here and I'm going to look up what t-score I need to be at that level of confidence with that sample size. And the sample size was 25 minus 1, 24 degrees of freedom, and that's 2.064. So my t-value that I need to exceed, I'm going to call that t critical. That critical value has to be 2.064, right? So if they're not that far apart, I can't say with that level of certainty that I want that the two means are really different. So how far apart were they? They were only 1.5 standard errors apart, 1.5 t-scores apart. So what did I need to reject the null hypothesis? I needed that to be bigger than 2.064. So can I reject the null hypothesis? No, I can't. So all I can say is I fail to reject the null hypothesis. I don't have enough evidence to say that these two are different. Now, let me look at this from another perspective. Let's say if instead of 97, this had been 95, right? Well, what would this have been if this had been 95? Well, 95 minus 100 would be minus 5, and this value would be negative 2.5. Now can I reject the null hypothesis? Right? My t-value is bigger than the critical value of t that I need for that sample size, so now I can reject the null hypothesis and reject the idea that they're equal and accept the alternative hypothesis that the mean blood pressure for population A is not equal to the mean blood pressure for population B. Okay? Okay, so, and that's as hard as this gets. I mean, you can do the same thing exactly that we did here with proportions, right? Do the same thing with proportions. The only thing is that there's p's instead of x bars. Okay, how are you guys doing online there? Questions? I don't see any questions online. Okay, good. All right, so now we're going to take this another step. Next step, which is what we're moving into now, and the way that this is going to be used the most, is the idea that we have two samples instead of one sample. Okay, things get a little complicated when we have two samples. And I'm going to open up a document that I have here. Okay, let's see if I can't find it now. Paired sample test, hypothesis testing, t-test variations. Okay, so I think I may have this posted to Blackboard. If I don't, I'll make sure it's up there tonight. But You've seen this before? Oh, good, excellent. I'm glad to hear that. Okay, so now let's say I take two samples, right? When I took one sample, I had a number and I was comparing it to a sample value and a sample standard deviation. I only had one standard deviation. The only standard deviation I had was for the sample. So that's the one I had to use. Now let's say I take two samples. If I take two samples, I have a little bit of an issue now. Which standard deviation do I use? Do I use the one for population A, or do I use the one for population B, right? For sample A or for sample B? Well, now you got to make a decision. There's two ways that we might handle this. One way is if the standard deviations are assumed to be equal. In other words, let's say I sample population A in the previous problem. I take a sample from population A, take a sample from population B. I get a mean and a standard deviation for population A, mean and a standard deviation for population B. If the two standard deviations are pretty close, maybe I say to myself, they're so close and there's no reason for them to be different. Let's assume both standard deviations are equal. Well, if you assume that they're equal, you could actually say to yourself, well, the 25 samples that I have from this group and the 25 samples I have from this group, why don't I combine them and get one more accurate standard deviation, which is kind of like having one for 50 people instead of 25, right? So we kind of find a weighted value for the standard deviation based on assuming that they're equal. Okay, and the way that we do that is that that we create a pooled standard deviation. And what's the pooled standard deviation? How do we calculate that? We take the standard deviation, we take sample size 1 minus 1, kind of like our degrees of freedom, times the standard deviation squared, the variance that's called, for sample 1, plus you do the same thing now, sample size minus 1 times. It's a little intimidating, right, looking at that, but it's really pretty simple. If you just follow standard deviation squared for sample 2 times n minus 1 for sample 2, in the case of 25, 24, over the two sample sizes, 25 and 25, if they're equal, 50 minus 2, 48, right? So you calculate that and then you find the square root of it. That gives you a pooled standard deviation. So now to calculate your t-score to see if they're far enough apart, you use the difference between the two means, x bar 1 minus x bar 2, and divide it by the standard error. What's the standard error going to be equal to? It's going to be equal to your pooled standard deviation times the square root of 1 over the sample size 1 over 25, let's say, plus 1 over 25. Right? It winds up being 2 over 25. So you calculate that t-score. You go to the table, now you have to look up the value you need to exceed with that t, the critical value for t, the value you need to be bigger than, right? You look that up on the table, but you need to know what degrees of freedom to use. So you had 25 in one group, 25 in another group. The number of degrees of freedom that you use is equal to n1 plus n2. In our case, as I was describing it, 25 and 25 is 50, right? Minus 2, one for each, right? One for each group. So 48 degrees of freedom. Okay, that's the degrees of freedom. If you go to the table, 48 degrees of freedom, you'd have to exceed 50 is the closest. You'd have to exceed, say, 50 is 2.009 in order to reject the null hypothesis that mean for group 1 is equal to mean for group 2. Now that's the first time really that we've, in person together, live, have discussed doing that by hand, right? It's a little intimidating, right? Because there's a little bit of math involved. How about you guys online? Did you guys follow that for the most part? Okay, it's pretty straightforward, right? It's not real complicated. A little bit of math involved, but if you're careful, you'll be able to keep it straight. Now, what about if the two standard deviations are drastically different? Let's say I take 25 from this group, 25 from this group. The standard deviation for this group comes out to be 5. The standard deviation from this group comes out to be 15. Usually drastically different. I usually would consider it that way if one is more than double the other, right? So in that case, 5 and 15, they're pretty different, right? So in that case, I can assume that they're equal variances. So what do I do then? Well, the next page has formulas that you would use to deal with that. Okay, so now don't look at that formula yet. Don't worry about that formula. Don't, you're not really gonna ever use that formula. Okay? So how are we gonna do that? Well, that's actually simpler. Don't ignore that formula for a second. That's actually simpler because the reason why it's going to be simpler, let me blow this up a little bit, is because the t-score is going to be calculated using this formula for unequal variances. The difference in the two means, easy enough, right? Like for us, it was 95 versus 100 minus 5 over the square root of the standard deviation for sample 1 over the sample size of 1 plus the standard deviation squared for sample 2 over the sample size for sample 2. Add them together, find the square root, and then divide that into the difference, which was 5. And that's how you calculate your t-score, right? Now, the oddball thing here is calculating the degrees of freedom. And you calculate the degrees of freedom by using this formula, except nobody really uses that formula. For most of the time, you're going to be using SPSS or some other software to calculate this. And if you're not, a good workaround is just to take the smaller of the two samples, subtract 1, and use that as your degrees of freedom. Because that's extremely conservative. It's always going to be more than that, right? So in other words, 25 sample size, 25 sample size, 25. Take 25, subtract 1, use 24 as the degrees of freedom to look up on your table what your critical value of t is going to be. We already used that. I think it was 2.009 or something like that, I think, right? Or 2.0, yeah, 2.009. So you don't have to really use that formula. But you see, this one's even, when they're unequal variances, in a way, it's kind of even simpler if you ignore the fact that you have to do that degrees of freedom operation. Okay? And with proportions, you similarly do the same thing. Okay, this is how you would calculate. Remember, use z. Now you're looking for it to exceed a critical value of z. What do you think that a critical value of z would be that you need to exceed to prove that two proportions are different? Remember the z, we use the z. Remember with the proportions, we use the z-score. So what do you think for 95% certainty an alpha equal 0.05? What do you think z has to be bigger than in order for you to reject the null hypothesis? Well, when we think 95%, what value is z we always think of? 1.96. So you have to exceed. And how do you calculate that? It's the proportion 1 minus proportion 2. In other words, if one sample gives you a proportion 15%, the other gives you a proportion of 20%, that'd be 0.05, the difference, over the square root of the p cap over here. P cap is a pooled proportion, which is the proportion 1 times the size of sample 1 plus proportion 2 times the size of sample 2 divided by the total number of people in that group. It's really the average, the weighted average of the two proportions. So you take that p cap times 1 minus p cap over 1 over n plus 1 over n2, right? And that would give you your standard error, and you divide that into the difference between the two proportions. Okay? I'm not going to bother to work that out because we just don't have, I won't work one of these out because we just are not going to have the time for that. But what I will do now is give you an example of this using SPSS or Excel. Okay, let's see if we have panic online here. Any panic going on online? Right? Shouldn't be any panic, right? I mean, it's a little convoluted, but if you just stick to the formulas and are careful about what you substitute where, you should be okay. And I think I might have posted, did I post an assignment 6 yet? If I haven't, it will be up soon. And assignment 6 will give you some chances to practice this a bit. Okay, so I'm going to go find an example of this. Okay, so let's see. Two sample t-tests. Okay, so here is an example of this. Okay, I got to wait for Excel to heat up, warm up. It's like, there we go. Okay, so whatever this represents, these numbers represents, maybe it's a number of soccer goals per season or something like that. But they're separated by gender. So this is the average for male. This is the males. There are 9 subjects, 9 males, 9 females, and this is X bar, not a proportion, right? So if I want to calculate the average, okay, we don't know what the population average is. We probably will never know, but the average for this sample is 10, and for females, the average is 7.5. So now my null hypothesis is: does the true mean for males equal the true mean for females? That's my null hypothesis, is going to be that they're equal. Mu for males equals mu for females. My alternative hypothesis is that the two means are not equal to one another. So how would I actually go ahead and solve this? Well, I would use I would then calculate my standard deviation for both of these. Okay, my standard deviation for males is 2.7, and my standard deviation for females is 1.94. Remember, what general rule did I give you before? That in order to say that they're unequal, that you probably would want them to be one at least double the other. So it's not quite double the other. So I would assume, make the assumption that the standard deviations are equal. So I would use the formulas on that first page where we're working with equal standard deviations. Okay, and we would we look at the difference, right? The top of the formula is going to be the difference, our t-score, and it's going to be t because it's a numerical variable and it's a small sample. Our t-score is going to be equal to, the numerator is going to be equal to the difference between 10 and 7.5. And the bottom is going to be equal to our standard error. If I go back to that page, what is our standard error equal to? If I assume I'd have to calculate a pooled standard error, right, which is n1 minus 1 is 9 times standard deviation squared. I have to take standard deviation for males, square it. N1 minus N2 minus 1 is 9 for females, times the standard deviation for females squared, over 10 and 10 minus 2 is 18. That's my pooled standard deviation. I'd substitute that in there. This would be 1 over 10, 1 over 10. This would be the difference, 7.5, 10 and minus 7.5, and we would find what our t-value is. And if our t-value exceeded 1.96, we would reject our null hypothesis. Now, instead of doing this in Excel, right, since I only have a few minutes left, let's do it in SPSS. So you may have noticed that in that folder, and I'm going to check so you make sure that somewhere that you have access to this when I post the video. Okay, in that folder is also the same sample, two sample t-test, two sample t-test. Here it is, two sample t-test.sav. Notice I gave you another example there where they had unequal variances. But I'm going to work with this one first. I'll start up SPSS. Okay, I'm going to open that file, open, data, and I'm going to look for, what folder was that in? That folder, I got to go to my desktop. Desktop is here, and the folder, what was the name of that folder? Thursday review, here you go. And two sample t-test. Okay, that's the variable view. The numerical view, notice this is females and males. I think they should be all the same numbers that we've had in the Excel file. Notice that the format of the file is different, right? In SPSS, we don't put it in two separate columns for males and females. Gender is one variable, and the score is the other variable, right? So if I want to calculate, if I want to compare the means of these two populations, my null hypothesis is that the mean value for females is equal to the mean value for males for the entire population. Remember, it's mu for females equals mu for males. Our alternative hypothesis is that mu for females does not equal mu for males. So now, in order to reject our null hypothesis that they're equal and accept our alternative, in other words, prove that they're different with that the level of certainty that I want, alpha is 5% or only 5% chance of being wrong, right? In order to prove that, I now have to compare the two means, see how many standard errors apart they are, in other words, what their t-score distance is, and compare that to the critical value for t for that particular sample size. Okay, so for you guys remember what degrees of freedom I use for equal variances, which is I'm assuming in this case, and for equal variances, and for 10 males and 10 females. What sample size do I use for my degrees of freedom? What 18, right? Great. 18, 10 and 10 minus 2, right? Okay, so let's do this analysis. Analyze. I'm going to go to compare means because that's what we're doing. What we did before was one sample t-test. What we're doing now is independent samples t-test, two samples. Okay, so I'm going to move the scores, the values, into my test variable. I'm going to move gender into my grouping variable. One of the things I forgot to do was to take a look in my variable view to remember what males and females, what numbers represented them. What's 1 and 2. Okay. Okay, so I have to let SPSS know that the grouping variables are 1 for males and 2 for females. Okay, it doesn't do that on its own for some reason. Okay, so I'm going to click OK, and it does the calculation for our descriptive variables and for our t-scores. Okay, so now notice that this top line says equal variances assumed. That's what we said we were going to do. So I'm going to go across this line. This first part, this is only a separate, notice a line goes up here. This is separate. This is only for testing whether you should use equal variances or unequal variances, right? So we've already decided we're going to use a top line, so I'm not going to bother looking at that for right now. So I'm going to go across here. So what is our t-score equal to? 2.184. Okay, 2.184. For 18 degrees of freedom, and notice it says I'm sorry, it was only 9 and 9. So it's 16, not 18. Right? Only 9 and 9. So for 16 degrees of freedom, what should be our critical value at t for 16 degrees of freedom? 2.12. Right? Can you see that there? 2.12. Right? 2.12 is our, so we want our t-score to be bigger than 2.12 to make our level of certainty better. In other words, exceed have less of a chance of being wrong than 5%. Okay, so let's see what we wind up with in SPSS. So we wound up with 2.184, which is bigger than the critical value 2.12. So we can reject our null hypothesis, right? Because our calculated t-score is greater than our critical value at t. Right? The bigger the value of t is, the less uncertainty that you have if you reject the null hypothesis. Now, SPSS not only gives us the t-score for us to compare to the table, but it also calculates a significance, or what we usually call a p-value. You see here where it says significance two-tailed? It's giving us not just that the t-score is big enough that our chance of being wrong is less than 5%, but it's actually quantifying our chance of being wrong. And what's the chances that we're wrong if we reject the null hypothesis? It's 0.044, 4.4%, which is less than our tolerable level of error, which is 5%. So because the t-score is bigger than the critical value, and the p-value, the probability of being wrong, is less than 5%, it's 0.044, both of those go together, and we can reject the null hypothesis and say that they're not equal. The mean for this population is not equal to the mean for this other population. Okay, are we certain of that? Well, no, we're never certain, right? We're 95% certain. We think there's less than 5% chance that we would be wrong if we make that statement. Reject them. Keep in mind, If that had exceeded, if the t-value had been smaller than 2.12, then our p-value would have been more than 5%, the way when SPSS calculates it. And both of those would indicate you failed to reject the null hypothesis. So in that case, you're done. You don't say anything else. You either fail to reject the null hypothesis, done, or if you have the evidence that you can, you reject the null hypothesis and accept the alternative hypothesis. Okay? I know there's a temptation to say, well, I failed to reject the null hypothesis, therefore I accept the null hypothesis, but you don't. You're not really, you're not testing that, and you really haven't proven that the null hypothesis is valid, right? You fail to have enough evidence to reject it, so you wouldn't say that. Okay, so let's call it a day. I'll put these examples up. You can practice with them and stuff like that, and hopefully that'll make some sense as we move on. And as we move on to the homework that involves these kinds of examples, okay, you guys will get back into the practice of using SPSS. Okay, and we'll be dealing with lots more examples of this coming week. Okay, good night, guys. Bye.